Hey gang, welcome back. We're going to pick up where we left off. Let's consider this lecture 8 part 2. Today we're going to talk about something called the paired samples t-test. So for the paired situation, when you have data paired, like the before and after kind of effect, where you take the same group of people or items, measure something about them at one point in time, and then measure something about them again later on, we do something called the paired samples t-test. So the target parameter here is still mu1 minus mu2, okay? Which we'll assume is there's no difference, or we'll assume that both means are the same, so that when you subtract them, this equals 0. All right, so that's pretty much very similar to what we were doing before. The estimator here is what we're going to call d bar, or the average of those differences. So basically what we're going to have here is we'll have a column or column or row of data from the before picture, and a column for data from the after. And for each one of those participants, you're going to have a so let's say you have sample the before sample, well, I'll call it and an after sample. It could be like year 1, year 2, whatever you're trying to measure about it. And you'll have a group of data in group 1, say 2, 4, 7, 9, 11. Over here, and maybe over here, you've got some numbers that either went up or down after the time period. So say 3, 1, 8, 6, and maybe 10. All right. Your difference is really your values for each row, the difference for each value in each row. So 2 minus 3 would give you -1. -1. 4 minus 1 would give me a 3. Get another -1. 9 minus 6 will give me a +3. Looks like I almost planned this out. 11 minus 10 would give me 1. And so what we would do is we would find the average difference here would be the averages of this last column. And so that's what d bar is. It's the average difference overall for all the participants in the group. They're the differences of every individual in the group. So this, you'd think about the first row represents individual 1, person number 1, person number 2, so forth and so on. All right. So that's what d bar really is. And then the standard error is just, this looks very familiar to the one sample hypothesis testing we did, because that's basically what paired samples t-test is. It's a one sample hypothesis test on the differences between two samples. Okay, and so we get a standard deviation of those differences, which we call S of d bar, or S of d. All right. And then we divide it by the square root of n, and we get our standard error. So this looks very much like a one sample t-test. It's really the same thing, with the exception we're really getting an average of the differences. All right. So the confidence interval formula looks very similar to a one sample variety. We take our point estimate, which in this case is d bar, our t critical value, and then our standard error, and we plus or minus that d bar plus or minus the critical value times the standard error, and we get our endpoints of our confidence interval, the possible where our population mean value for the differences would lie. Okay. And so it's pretty much like we've been doing with every confidence interval. That's how we would construct one. Okay. To do the test statistic for the paired samples t-test, excuse me, we would do the d bar minus 0, because we're assuming that there's no difference in the population means here, and then divide it by the standard error. So it's a pretty easy calculation. You just have to get that value of d bar first. So if you had to do it by hand, that's how you'd calculate the test stat. All right. The notation for here, very similar to what we did with a one sample hypothesis test. Basically, we're taking two samples and we're creating one sample made up of the differences, as we noted before. All right. for each participant in the study. We usually note the population mean for the paired difference as mu sub d. All right. The order of the groups is usually decided on by the researcher. So the order you subtract these guys in is very similar to the order you decide to subtract them in, because it's going to tell you a lot about the differences or not. What often people will do in practice is they'll put depending on what their alternate hypothesis is, they may put the group, they may make their first group the before versus the after versus before. If they're trying to look for an increase or a decrease, it's going to be important in the way that what order you put these guys in, because it's going to subtract them in that order. And so if you get a negative value, that's a decrease. But depending on how you put those in what order, and what you're trying to find out, that decrease may be a good thing, or it could be a bad thing. So you have to be careful with the study you're doing, and the order. You just have to pay attention to how you analyze it at the end. We'll see some examples of that. We'll assume the population mean for the paired differences is 0. All right, so for our hypotheses, we'll use 0 for our population mean. Implying there's no difference. People can use values other than 0 in this test. If there's a known value that that the difference between a before and after group or between a paired grouping of data is, then you can use that rather than 0. You're trying to prove the difference is something else. So that's possible. We'll use 0 in this class for these hypotheses because we're going to stick to that for the most part. Okay. And then again, you got your left-tailed, your two-tailed, and your right-tailed tests. And they follow the suit of the hypotheses we've seen before. So if you do a paired samples t-test and ask you for the null and alternate hypotheses, or for you to state your hypotheses, you need to decide on which one of these guys is the correct one to do. And this is the notation I want to see in your R projects. All right. So again, we have a less than, not equal to, and greater than 0. All right. So if we think the difference is increased over time, we'll do a greater than. If we don't know, we'll do a not equals. And if we think the difference between the two groups is decreased from before to after, then we'll do less than. All right, so let's look at this one. A group of 10 women aged 16 to 49 who are not on birth control were asked to participate in a study to see if oral contraceptives, we'll call it OC from here on out, had an effect on their blood pressure. All right, the researcher measured the systolic blood pressures in millimeters per mercury of these 10 women prior to them starting on OCs. So we got a before measurement of them when they're not on the OCs. The researcher reassessed the blood pressures of the women after being on the OCs for a full year. I'm giving you the data set in the R code only file. It's called OC_SPB. So that stands for oral contraceptive systolic blood pressure, and can be uploaded using the code HYPE, using the code that's in the R code only text. We'll do this in a minute anyway. Test the hypothesis that the SPB levels for women after using the oral contraceptive is different. So we're doing a not equals variety test, a two-tailed test, from before using the contraceptives. So we want to know if there's a difference. The researcher also wants to calculate a 90% confidence interval for the true increase in mean SPB after starting OCs. Okay. And so we're going to do that next. So my hypotheses here, my null hypothesis is the population mean of the difference is equal to 0 versus that's not equal to 0 for the alternate. In the t-test function, there's another argument we can put in there called paired equals true. Usually this is set equal to false, which is why we don't have to put it in there. But if we want to run a paired t-test, we have to put this inside our t.test function to get it to run a paired t-test. This is a very useful function. It does several different things. So let's do that in R real quick. I want to get the data in there. I think you guys are probably starting to get the hang of how to do this. But let's get that oral contraceptive data set in here and attach it. SBP, yes. All right, let's take a look at it before we do anything with it. So we've got two columns of data here. One's systolic blood pressure when not on OCs, and the other one's the systolic blood pressures when they are on OCs. So those are our readings, and we're going to see if there's an increase here in a moment. So that's important to note these two, the names that are given for these data values here, because we're going to have to use those verbatim when we plug them in. All right. So in the t.test function, since I'm doing a 2-sample t-test, I can also get my confidence interval. Then they wanted us to do a 90% confidence interval as well, so we can do that in here too. So let's plop that in there. Notice I put SPB yes, because and I did that mainly because it says true increase here for the confidence interval after starting using the OCs. So I put that group first. I'll show you that you get similar results regardless of what order you put these in. All right, so let's run this. I've got paired equals true. The conf dot level set equal to 0.9, and then of course I made sure that my variables are in there in the correct order, and I hit enter, and here's what it spits out for us. So the p-value is very, very small, which tells me that there is a difference between the oral contraceptives. All right, so they are different. There's before and before taking them versus after taking them. Looks like it may have increased them, but we can't say they increased them. We just can say they're different based on the hypothesis test we ran. But the confidence interval gives us an idea. Since both of these values are positive, there was definitely an increase in the SPBs after using the OCs. That just sounds weird to say, sorry. Anyway, so if you'd run this test with these two variables reversed, so let's do that and see what happens. So let's say I changed this to no. Let's just take the no here out, and I'm gonna put it in front of the PV. Let's see what happens. Do we see any difference here? Not really. We still get the same p-value. The test statistic value that we got is negative instead of positive, but it's identical in value. All right, and then the values here are negative and negative. So much like in the 2-sample independent test, when we put the yes group second, this means that the yes group had a that relates to the fact that both confidence interval values are negative. Relates to the fact that the yes group had higher blood pressures than the no group. All right, this is kind of a known fact that oral contraceptives in women do have a tendency to increase systolic blood pressure, but and that's what was going on with this study. When we had the yes in front of the no's, or going in first, so it was like we took the values from the yes group and subtract from the no group. We again get both positive values, because that's when the first group is bigger, because our larger values are coming out of it on average. All right, so that tells us a lot about the order of these things, and if you put them in the order, you have to pay attention to what group you put in first and second, just like you did with the independent samples T, because it tells us the same kind of thing, which if they're both negative or both positive, it tells us something about the before versus the after. And so you have to pay attention to that order when you interpret this stuff, so that you don't mess that up. Okay. So what's important to pull from our paired samples t-test? Things to take note of here is that the p-value is 0.008874, and the 90% confidence interval is that 2.153424 to 7.446576. And if I were doing this correctly, I'd put mmHgs after this. You can't do that with R, unfortunately. You can do it in a separate write-up when you do your interpretation, though. So with that small p-value and that 95% confidence interval, we can conclude for the hypothesis test conclusion, since p is Since our p-value is between the 0.001 and 0.05 level of significance, we reject the null hypothesis. There is strong evidence to conclude that the population mean SPB levels, SBP, I feel like I said SPB, after using oral contraceptives does differ from before using the oral before using the oral contraceptives. So the order I put them in there was important. So after using versus before using. The interpretation for the confidence interval, obviously we see an increase with that as well. It says we are 90% confident that the increase in population mean SPB levels for women after using OCs is at least 2.2 millimeters of mercury, and at most 7.4 millimeters of mercury larger than before going on OCs. When we go back to here, for when we get a one-sided, like everything's either positive or negative, we're going to be talking specifically about the one group being larger than the other. And so this is somewhat similar to the independent samples t-test interpretations, but it's more like the one sample ones we did back a few lectures back. So this is not that cheat sheet is not as helpful here, but it is helpful to know that these values up here represent the after use group. All right. Let's do another example. Example 5, we have a crossover trial as a type of experiment used to compare two drugs. This is done a lot by drug people who make different kinds of medications. Subjects take one drug for a period of time, then switch to the other. All right. So the responses of the subjects are then compared using matched pair methods, or just paired methods, if you will. In an experiment to compare two pain relievers, 7 subjects took one pain reliever, we'll call it drug A, for 2 weeks, then switched to the other drug, drug B. They rated their pain level from 1 to 10, with the larger numbers representing higher levels of pain. All right. The results can be found in the R code only file. I won't read that whole sentence. The researcher wishes to run a hypothesis test to test whether the mean pain level, that's what we're interested in, mean pain level is less with drug B. All right, so we're curious if it's less with drug B. She also wants or wishes, I don't need wants, wishes to construct a 99% confidence interval for the mean pain level. So since we're doing a less than test, we're going to have to run the t-test twice here, because we're not going to run the 99% confidence interval on a less than or greater than test. So let's do the hypothesis test stuff first. And so if we state the hypotheses, we got the mean difference, population mean difference is equal to 0, and this actually shouldn't be equal to 0. This should be greater than or equal to 0. That's a typo. Versus the alternative, which is mu, the difference, population mean difference is less than 0. Okay. Again, we'll run our t-test with the paired equals true, and we'll get the following. All right, so if we import that data set in there, drugs, and I'm going to do it over here so we can look at the data set real quick, because I think that's always important. Let's see here. Drugs. There we go. That's what I call this data set, just simple old drugs. So pop that in there. We'll attach drugs in just a second. Drugs came up awfully fast. Let's see. Attach drugs. And let's take a look at drugs real fast. So we got drug underscore A, drug underscore B, and we want to see if the pain reliever is less with drug B. All right. All right. So it looks like it might be, but it may not be. Those numbers are kind of close together in the pain scores that were given there. All right. So these are scores on a pain scale. They don't really have units because they're scores, so we don't have to worry about units here. So if we run our t-dot test using alternate equals less, since I wanted to know if drug B's were less than drug A, right? That's really what I want to know. Are they less than drug A? I put drug B in first here. That's kind of an important distinction. Now, you could have done it the other way, but then your alternate hypothesis would be that the drug A has to be greater than drug B pain levels, and that would make sense. So you can do this more than one way. All right, just be careful how you interpret it. But when we do it, we see that we get a P level of 0.11, which is not significant, okay, at all. And that's really the only important thing we can take here. And we were given a 95% one-sided confidence interval, so we're not going to read that. All we care about from this particular thing is that the p-value is 0.11, and we're not going to reject the null hypothesis. All right. All right, we don't have enough proof to say that drug B is definitely gives a less, the mean pain level is less for that drug than for drug A. All right, so the things to kind of take note of here is the p-value is 0.11, and that we didn't get a 99% confidence interval because we got a one-sided 95% one. So we're gonna have to run the t-test again and do a two-sided test this time, so we can just actually call up the one we had, if it'll let me get in there. There we go. Instead of less, I'm gonna change this to two-sided, and after that quote, that single quote, I'm gonna add a what is it, conf.n, I believe, conf.level equals 0.99. Yep, and so then we hit enter, and we get this, which we will see on my next slide. And we see it goes from negative to positive. All right, so let's look at that. So I've got negative 2.64 right here to 1.219. I kind of expected this because we rejected, even though it was a one-sided test, we were doing a rejection. Notice the p-value if we'd done a two-sided test. In other words, if we said if we were trying to prove that there was that the two populations, the difference wasn't equivalent to 0, we would reject that too. All right, so we couldn't prove that they weren't the same. And when that happens, often you'll get this negative to positive value, just like we did with the two sample, the independent two samples test. This happens a lot. When you don't reject the hoe here, often you'll get an inconclusive result, which gives you the negative value to the positive value. And this means very similar things, that the difference, if one of them is very different than the other, then it's by at most a certain value, and vice versa. So we put drug B in first, and then we put drug A in second. So things to take note of there is that those two values represent our 99% interval, and now we just need to come up with a conclusion for our hypothesis test and an interpretation for our confidence interval. In the R projects, I will ask you to do these things in separate parts, so you won't ever do these things all together at one time. So just let that be known. So again, when we ran our one-sided t-test, our paired t-test, we got a p-value of 0.11, and then our confidence interval, I went ahead and did some rounding here, went from like roughly -3 to 1. All right. So since p is actually, that's not supposed to be less than. I have a bunch of typos in here, and I apologize. I'll hopefully have fixed these by the time you guys see this. Since p is greater than the 0.10 level of significance, we do not reject the null hypothesis. There is no significant evidence to conclude that the population mean pain level is less for drug B. All right, so we have nothing to say at all that it's less. All right, simple, quick, easy conclusion. The interpretation for the 99% interval would be we are 99% confident that the population mean difference in pain level is between -3 and 1. All right. Since 0 is contained within this interval, we cannot determine whether there is a difference in the mean pain level for drug A and drug B. So unlike the independent samples t-test, when we got a negative to positive value, we could say that one group would, if it's larger, would be by at most this, and the other group, if it were larger, would be by at most the other value. We don't do that with the paired samples t-test. We just go, the results are inconclusive. We don't have enough evidence to say that one's really truly bigger than the other. It helps them when when the hypothesis test also does the same thing. All right. In this case, I know we're treating this a little differently than we did the other one. It's just common practice for this particular test, so we'll kind of stick with this kind of write-ups when we do this. But that's pretty much it. I think this lecture went fairly short. I don't think I kept us in here too long today. If y'all have any questions, we'll be here Thursday night to talk through them. So hit me up Thursday night with any questions you have, or an email, and we'll talk to you guys later. Hope everybody's doing great.